All right, good morning, class. This is lesson 20, starting chapter 5. We're looking at section 5.1. So as promised, as we get into chapter 5, this is going to start pulling together everything we've learned so far in this class, and we're going to utilize everything we've learned, all the different pieces, all the different vocabulary terms. All of these things are going to help us solve some of the problems we're going to be trying to work out later in chapter 5. But when we start chapter 5, we need to introduce some new terms. We need to talk about some special vectors, why they're special, why they're going to help us, and then we're going to use these special vectors more so as we continue in chapter 5. All right. So this is section 5.1. So what are we talking about? Well, if you've heard of them before, we are talking about eigenvectors and eigenvalues. What are these things? Well, I think to start, let's look at an example. And of course, we're going to look at the matrix equation because that's what we've been doing the entire summer class. So consider the matrix equation AX equals B with A equal to the matrix 3, -2, 1, 0, and let X be the vector 2, 1. Okay, so I've given you a matrix, I've given you a vector, and let's just see what happens when I multiply them. What's my output? What do I get from this equation? So A times X equals my matrix times my vector, and we're going to get 2 times 3 is 6, minus 2 is 4, and then we're going to get 2 minus 0. We get 4, 2. Okay, well, that's easy enough. I mean, so far, what's the big deal? This seems just like what we've been doing all along. Well, there is something special happen here. Notice this pattern where what was my output? Well, it turns out my output is a multiple of my input. In fact, my output here, the output vector B, was 2 times my input. So for this very specific example, for this specific A and for this specific X, we have, so A times X equals 2 times X. Interesting. Something about this matrix and something about this vector turns out that when we transform it, we're really just getting a multiple of what we plugged in. Okay, so this is a little different than what we've been doing. And in fact, this is exactly what it means to be an eigenvector and an eigenvalue. This is what an eigenvector looks like in practice. So let's get our definition. Let A be an n by n matrix. So notice what we're about to talk about. This is a phenomenon which only occurs for square matrices. Why? Well, if I want my output to be a multiple of my input, that means my output and input are in the same space. Well, if my output and input are in the same space, A has to be a square matrix. This is the only way this can happen. So you can only have eigenvectors and eigenvalues for square matrices. If it's not a square matrix, then it is impossible to have eigenvectors and eigenvalues. All right? Then a vector x, which is not equal to 0. We can't have an eigenvector which is 0. X has to be not 0. X not equal to 0 is called an eigenvector. If A times X is really just some multiple of X. We're going to use the Greek letter lambda, lambda times X, where lambda is a constant. All right. Now notice, I'm not saying lambda even has to be a real number. I'm just saying lambda has to be a constant number. And part of highlighting this because it means in some applications, lambda can be an imaginary number. Now, for the sake of this class, are we really going to deal with that much? No, not really. It's more of an advanced topic. However, again, in other classes, abstract linear algebra, or some other physics engineering courses, you can certainly run into this, right? You can have an eigenvalue which is imaginary, or you can have a lambda which is imaginary. So lambda is a constant scalar, right? So we have an eigenvector if, when we multiply it with a, we actually get out a multiple of the original vector we plugged in. In this case, lambda is called the eigenvalue. So what we see here is that eigenvectors and eigenvalues come in pairs with one another. If you have an eigenvector, that means you automatically have an eigenvalue associated with that eigenvector. Because in order to have an eigenvector, that means your output is a multiple. Well, if your output is a multiple, the eigenvalue is whatever that scalar multiple is. And vice versa, if you have an eigenvalue, that means this equation happens, in which case that means you have an eigenvector. So eigenvector and eigenvalues always come in pairs. Sometimes you might only be given one or the other, and you have to solve for the other, but they always come together, right? So x is an eigenvector corresponding with lambda, right? They come in pairs. So the last thing I want to highlight here is if we go back to the example up above, well, then in the above example, the eigenvector was the vector 2, 1, and the eigenvalue, lambda, was 2. Okay? So we had that first example. Now, we haven't talked about how to find eigenvectors and eigenvalues yet. But before we do that, you know what? Actually, let's go ahead and do that next. So let's look at this next example, try to understand how to find eigenvectors and eigenvalues. We have this example of one that occurs, but we don't know, how do you know if a matrix has an eigenvector or not? Or how do you know if something is an eigenvalue or not? All right? And it's all going to boil down to using the fact that when you have an eigenvector or eigenvalue, that means this equation happens, right? If you remember nothing else from today, remember this equation. This will be key to solving almost every question that involves eigenvectors and eigenvalues. If you have an eigenvector and eigenvalue, it means a times x equals lambda x, always. Use this fact, and it's going to help you solve for whatever it is you're trying to find. All right? Okay, so let's look at an example. All right, now for this case, I'm going to give you a matrix again, and I'm going to give you the eigenvalue, but I'm not going to tell you the eigenvector. We're going to have to find the eigenvector. All right, so let A equal 1, 6, 5, 2, and we're going to say show lambda equals 7 is an eigenvalue for the matrix A. All right, so I'm already telling you what an eigenvalue is. Now the question is, how do I find its eigenvectors? What does this mean? What do I do? Okay, well, don't panic. What did we just say before when we had the definition down here? Use the fact of that equation. The fact that this is an eigenvalue means that there exists an x such that a times x equals 7 times x, right? I'm just using the definition of an eigenvector and eigenvalue. Do I know what x is? No, but I can solve for x. All right? Okay, so what can we do? Well, if I'm trying to solve for x, just like regular high school algebra, I need to get x on the same side. Now, what's a little bit strange here is that in previous matrix equations, we were trying to solve for matrices, but now we're trying to solve for a single vector. So I'm going to subtract 7x over, but I would like to get x by itself. How do I get x by itself? Well, I need to factor out a vector x, right? I have an x term and an x term. I need to factor it out to the right side. Notice, as we've kind of discussed before, the order of your multiplication matters. You cannot factor x out to the left side. Some students did on the midterm. That is wrong. You can never do that with matrices, right? You have to be very careful with the order in which you're dividing things out or factoring things out, all right? So how do we factor this x out? I have a 7 times x. What does that mean? Well, 7 times x, really it has an implied 7 times the identity matrix times x, right? The identity matrix times x is really just x. So these two are the same things. So there is an implied identity matrix here. It's just not written. Why am I bringing this up? Well, when we factor x out to the right side, we're going to have a minus 7i. Now I have x as a single x, and I can solve for x now. Well, how come? A minus 7i is just a matrix, right? I can figure out what that matrix is. This is just a matrix. In fact, this is the matrix where I'm subtracting 7 down the diagonal, right? I'm subtracting 7 down the diagonal because that's what I is. So this is 7007, right? So this matrix is -6, 6, 5, 2, minus 7 is -5. And you should notice a funny pattern of when you do this, if you've done it correctly, this matrix should turn out to be linearly dependent. Why? Well, we're going to talk more about that in a moment, not quite yet, but there is something special that's happening here. Furthermore, I also want to highlight, why do we have to do this 7i business? Well, imagine if the I wasn't there, then this would just say a matrix minus a constant. But do we know how to do a matrix minus a constant? No, we don't have any operation for that, right? I can add and subtract matrices. I can multiply a matrix by a constant, but we have nothing in our operations that allows us to add a constant to a matrix. So if I'm trying to subtract 7 from a matrix, I really do need this I here, because then it's a matrix minus a matrix, and that we know how to do, right? Okay, so I have this matrix. Now let me bring down the rest. Times x is supposed to equal 0. How do I solve for x? Well, rinse and repeat, going all the way back to chapter 1 again. Just take your matrix and augment with 0. All right. Now, at a first glance, trying to multiply 6 by something to get rid of 5 is going to get messy with the fractions. It could be easier if I just go ahead and factor a 6 out of row 1. So that's fine. That won't hurt anything. But now it's a little bit easier to see what's going to happen. I'm going to take row 1, multiply it by 5, add it to row 2, and we're going to get 0, 0, 0. And I am now in echelon form. Oh, and also, I don't recall if I ever explained the notation before. Whenever I do this little squiggly line between matrices, that means this is a reduction step. These two are row equivalent because I did a row reduction step to go from this matrix to this matrix. This is just saying that, like, yeah, this matrix reduces to this matrix, reduces to this matrix, right? That's all this little squiggly line symbol means. So I hadn't explained it yet. Okay, you can also see this notation is used in the textbook. At any rate, but what's happening here? I have a free variable, and this is consistent, so that's fine. We have a solution. But because I have a free variable, that means with this eigenvalue, I actually have infinitely many eigenvectors which correspond with it. Okay, that's interesting. So how do we find the eigenvector? Well, solve for my variables. X2 is free, and negative x1 plus x2 equals 0. So x1 equals x2. All right, so getting practice with the parametric vector form, super crucial for this step in the class. My vector x is a column vector of x1 and x2. So this is what I was suggesting for some students. On the midterm, write your vector as a single column vector, fill in the information. X1 equals x2. X2 is free, so that's x2. If you've done this step correctly, you should have a column vector which only has free variables in it. Okay? What's the last step? Factor out the x2. In other words, what are my eigenvectors? Well, my eigenvectors is any vector which is a multiple of 1, 1. All right. What else can we say about this, though? Well, these eigenvectors, we know from what we did in chapter 4, talking about subspaces and span and everything, that the set of these vectors x, this is the span of 1, 1. In other words, this is a subspace of R2. So the set of eigenvectors, which are associated with this eigenvalue, form a subspace, right? Now, because this is a special subspace, it's a subspace of eigenvectors, we're going to call it a eigenspace. All right, so let me write that out. And we can also double check, does this answer work, right? For example, if I let x2 be 1, okay, that means my vector x is 1, 1. Does this solution work? Well, a times 1, 1 equals 7, 7. And lo and behold, yeah, that is 7 times the vector I plugged in. So great, that works. Okay, so we're talking about eigenspaces next. So what does this mean? Well, for this eigenvalue, for lambda equals 7, there is a subspace of associated eigenvectors called an eigenspace. Called an eigenspace. So notice an eigenspace is not a single eigenvector. It is rather a set of eigenvectors. but it's a set of eigenvectors which all correspond with the same eigenvalue, right? So if we're only wanting, for example, linearly independent eigenvectors, well, then I only need to take one from this space. Or rather, I need to take however many I got from my solution here, right? In this case, my eigenspace, which notationally we're going to use capital E for eigenspace. And this is the eigenspace associated with lambda equal to 7, right? So that's the eigenvalue. So we'll use subscript lambda equals 7. Or you can just use subscript 7. The whole point here is that this is an eigenspace which is associated with an eigenvalue of 7. What is this space? Well, it is the span of 1, 1. And again, the notation of vocabulary is key here. If you leave out the word span, your answer is wrong, right? Because if you don't say span, you just say the set of 1, 1, this is now a finite set with only a single vector. But it's not a finite set. It's supposed to include all of these possible linear combinations because x2 is free. x2 can be any real number. So if I want to talk about all of the eigenvectors associated with this eigenvalue, I really do need the word span here. Okay. Now, what else can we say about this? Well, we are working in R2, so we can graph this. And in fact, this eigenspace is associated with the line, which is a multiple of 1, 1, right? Any multiple of the line of the vector 1, 1 is this line. So the eigenspace associated with lambda equals 7 is this one-dimensional subspace of R2. All right, so this is nice. We can also see when we discuss dimension that the dimension of E7 is 1. All right, that's great. What else can we do? Well, if I continue with this problem, we might like to know, well, is this the only eigenvalue? Are there other eigenvalues? How do I find out? Well, let's see, what does it mean to be an eigenvalue? All right. Again, to answer this question, we have to go back and think about what does it mean to be an eigenvalue from the definition. That means AX equals lambda x. And this is true, recall, for x not equal to 0. Right? There is a non-zero solution to this matrix equation. So now if I'm imagining, well, actually, I want to solve for lambda now, right? How would I do that? Well, if I subtract here, we're going to have AX minus lambda x equals 0, just like we did before. I can factor out the x. The x is on the outside now. But this has a non-zero solution. In other words, x is not 0. Or in other words, this homogeneous system has a non-trivial solution. Why? Because there's some x which is not 0, which is a solution. There's some non-zero vector, which is a solution for this homogeneous system. Again, going all the way back to chapter 1, right? All those vocabulary terms we learned, they're all still relevant here in chapter 5. Okay, so that means we have a non-trivial solution. In other words, the matrix A minus lambda I is linearly dependent. Well, what else does that tell us? that means the determinant of this matrix, A minus lambda I, is not 0, right? So we're actually going to find out, and I'm getting a bit ahead of myself because we're going to talk about this a lot in greater detail in wait, hold on. I believe I have a mistake here somewhere. Oh, I do have a mistake. Equals 0. Right, my mistake. Remember the invertible matrix theorem. To be invertible means the determinant is not 0, right? To be linearly independent means the determinant is not 0. If your determinant is 0, then that means your matrix is linearly dependent. It is not invertible. You're going to have a free variable, and your homogeneous system is going to have a non-trivial solution. So in other words, how can you find the other eigenvalues? Well, you can take the determinant of A minus lambda I, set that equal to 0, and solve for lambda. Now, for the sake of today's lecture, I'm not going to go into this in more detail because that's exactly what 5.2 is about. 5.2 is all about diving into and really dissecting this equation. So you got a little bit of taste for what's for tomorrow, but we're not going to talk about this today so much. All right. But my whole point here is that you can go through this process, blah, 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 blah. We'll talk about that tomorrow. But if you continue this process, note that we have a second eigenvalue. So when we have multiple eigenvalues, I'll use subscripts. Lambda sub 1 is the first eigenvalue, which was 7. Lambda sub 2, we have a second eigenvalue of -4. All right. And you can rinse and repeat, go through the same process as we did earlier. Find eigenvectors by solving A minus, well, in this case, because it's -4, it's a double negative, so plus 4i times x equals 0, right? Again, how do you find eigenvectors? It boils down to solving this matrix equation, which boils down to solving this homogeneous system, right? So very, very crucial from back in chapter 1, we were first learning about homogeneous systems. Okay. Go through this process, and if you want practice, you can check this for yourself, try to find out what these eigenvectors are. And what do we get? Well, we have a second eigenspace. We get a second eigenspace, E4, or sorry, -4. This is the eigenspace associated with the eigenvalue -4. And we find out for this eigenspace, it is the span of 6, -5. And just like before, we can graph these. So that means the second eigenspace, it's any linear combination of the vector 6, -5. Okay, well, that's something like this. But it's any combination, which means if I multiply it by a negative scalar, it can go in the reverse direction. And this is my second eigenvalue, -4. And it's multiples of the vector 6, -5. All right. So what's special about this? Well, we can see that these eigenvectors are linearly independent. Why? Well, these eigenvectors come from different eigenvalues. And in fact, whenever you have eigenvectors from distinct eigenvalues, you're going to have linearly independent eigenvectors. They're going to be going in different directions, in independent directions. So this is a fact that is always going to happen with eigenvectors from different eigenspaces. That's the key here. So long as you have eigenvectors from different eigenspaces with different eigenvalues, then those eigenvectors are going to be linearly independent. Which means if I wanted to, I could form a basis for R2 from these eigenvectors. Now I'm getting a bit ahead of myself. We're going to be doing that more later in chapter 5, but I just want to give you a little taste for, why we care about this stuff, how we're going to use everything we've learned so far, and what's going to help us build. We're going to find out that there's something very special about a basis when it's built out of eigenvectors, right? So this is a very special type of basis, which is going to help us do other things, which we'll talk more about later in chapter 5. Okay, so what else do we have in 5.1 then? Well, we have a couple of theorems, which are going to highlight everything that I just said. All right, so here we have this theorem. If V1, V2, ... VR, so I have an R number of vectors, but more specifically, let's suppose V1, V2 through VR are eigenvectors. Suppose these are eigenvectors corresponding to unique, this is the key here, corresponding to unique, or in other words, distinct eigenvalues. Eigenvalues, lambda 1, lambda 2, ... lambda r. So what we're saying here is, okay, let's suppose we have r different eigenvectors. And for each eigenvector, let's suppose each one comes from a different eigenvalue. So I have different eigenvalues have a unique eigenvector associated. That means each of these are going to be values. So that's exactly what we're going to say here. Suppose these are eigenvectors and eigenvalues for an n by n matrix. Again, the matrix has to be square. Then the set of my eigenvectors is linearly independent, so that's good. And we have that R must be less than or equal to n. Why? Well, because this is the number of linearly independent vectors in this case, recall that for like Rn, it's an n-dimensional space, right? We have an n by n matrix, so my vectors are inside of Rn. That means I can, since it's an n-dimensional space, think back to chapter 4 when we talked about dimensions, I can have at most an n-dimensional subspace, right? In fact, because it's n-dimensional, I can only have up to n linearly independent vectors in order to form a basis for Rn, right? In order to form a basis for Rn, that has to be a set of n vectors. But if I take more than n vectors, so think about R2. If I take 3 vectors, it's impossible to have 3 linearly independent vectors in R2, right? Because you can only have at most 2 pivots in R2. Same thing is happening here. For an n-dimensional space, you can only have at most n linearly independent vectors. So however many eigenvectors I have, they have an upper bound of at most n. I can only have at most n linearly independent eigenvectors. But it also could be, well, maybe I don't have enough eigenvalues. Or maybe I don't have enough distinct eigenvalues. It could be that, if I only have one eigenvalue, well, maybe that one eigenvalue only has one corresponding eigenvector. Well, in which case, I only have one eigenvector, or one, excuse me, one linearly independent eigenvector, and that might be smaller than, whatever the dimension of the space is. You could have examples of a two-dimensional space, such as R2. A is a 2x2 matrix then. And it could be the case that you have only a single eigenvector, right? Or at least only one linearly independent eigenvector if you only have one eigenvalue. And so in that case, 1 is less than or equal to 2, right? Because it's a two-dimensional space. N is 2 in that case, but R can also be less than. So we have this bound where R is less than or equal to N, okay? So we're not guaranteed to have N different independent eigenvectors. We could have fewer than that, but we could have up to N different ones, all right? Right, what else do we want to highlight here? Well, the last thing I want to point out is there's something nice that happens when we're working with triangular matrices. All right, what's special about triangular matrices? Well, kind of consider this example that we keep going back to. 1, 0, 1, 2, right? Now, we've already said earlier, if you want to find eigenvalues, that means you're trying to find, for this equation, a minus lambda I times x, we want a non-trivial solution. We need a non-zero x, which makes this true. Well, that means the determinant of a minus lambda I must equal 0. We said that earlier. In order to have a non-trivial solution, a minus lambda I must have a free variable. It must be linearly dependent, in which case the determinant of a minus lambda I must be 0. Okay, but what is this then? Well, the determinant of 1 minus lambda, 1, 0, 2 minus lambda, what happens? Well, recall when we were talking about determinants way back in chapter 2, again, all this stuff is going to come back together in chapter 5. When we're taking the determinant of a triangular matrix, right, all you need is the diagonal. In fact, it's what happens when you multiply the diagonal. Look back at chapter 2. The determinant of a triangular matrix is the product of the diagonal. Well, where does this equal 0? That happens when lambda equals 1 and lambda equals 2. But lo and behold, what is that? That was just my diagonal. So in fact, anytime you have a triangular matrix, there's no work to do. For every triangular matrix, the entries on your diagonal are your eigenvalues. So this will give us our last theorem for today's lecture. A nice handy trick involving triangular matrices. So let A be a square n by n matrix and suppose A is triangular. Okay? Then what can we say? Then the eigenvalues are the entries on the diagonal, which is exactly what we see happen with this example. They are the entries on the diagonal. Now, this does bring up an interesting point of, well, what happens if you have repeat eigenvalues? What if an eigenvalue happens more than once? Or what if you have a case where it's something like this, and now one of your eigenvalues is actually 0? What does that mean? Well, these are all special cases we're going to discuss more as we continue in Chapter 5. But for today's lecture, I really just wanted to introduce eigenvectors and eigenvalues so you can get a grip on what these things are, what they look like, how to find them. But as we continue in Chapter 5, we'll talk more about these kind of special cases and how to handle them. All right. So next, let's go ahead and look at today's participation question. So this is, let's see, let me share my screen. All right, sharing. We are looking at participation day 19. All right. If X is an eigenvector for A, the matrix A, corresponding with eigenvalue 3, then what does A cubed times X equal? Now, this one's kind of a funny little problem that doesn't take a lot of work, but it uses what we learned today. How do we do this? Well, I'm going to do this on the board. So I'm going to stop sharing the screen. And let's go back to the board. So the idea here is we already know that X is an eigenvector for A with eigenvalue equal to 3. Okay, what does that mean? Well, by definition, from what we have in class today, that means A times X equals 3 times X. Right? Everybody agree? Or you should? Well, I realize it's a recorded video. You can't say if you agree or not. That's more out of habit for when I'm teaching in person, then like I do ask you guys questions, but I can't ask you questions. Okay, all right. So what's A cubed? A cubed times X. Well, even though this is kind of funny looking, don't worry about that. We can pull this apart. This is A times A times A times X, right? That's what A cubed is. Not a big deal. But now, based on what we know from our definition, I can figure out A times X. So this is A times 3x. Now, what did we learn about matrices and when we're multiplying constants? Multiplying by constants is the one time you can flip around the order. Multiplying by constants is the one time that you can move the multiplication around. So because this is a constant 3, I can pull it to the outside. 3 times AX. Well, rinse and repeat. What's AX? Again, that's 3x. So I have 3 times A times 3x. Pull the 3 out. Now I have 9ax. But again, ax is just 3x. And we get 27x as a final answer. In other words, if you have your matrix raised to a power times an eigenvector, this is actually going to be your eigenvalue raised to that power times x, which is exactly what we saw happen, right? 3 raised to the third power is 27. So our final answer for today is 27x. Okay? So that's it for today's participation question. And that's all for today's material. If you have other questions, by all means, let me know. Email me. I do have office hours this evening at 6 o'clock. So feel free to come by if you have other questions, or email me if those office hours don't work for you. Otherwise, that's all for today. Best of luck. I will see you tomorrow.